Okay, section 1010 is all about buffer solutions. And a buffer solution is a solution which is able to resist changes in pH when you add acid or base. But in order to really emphasize why buffer solutions might be important, I wanted to do a quick practice example to show how much the pH can change with even just a little bit of acid added. So if I have 100 milliliters of pure water, then what is the pH? Well, if it's pure water, then the pH is going to be 7.0. If I add just 1 milliliter of 1 molar hydrochloric acid, then what will the pH be? Well, let's think about it. The 1 molar hydrochloric acid is essentially being diluted by about 100 times. So the 1 milliliter will be diluted to 101 milliliters when you put that drop into your water. And so that's close enough to be about a 100 times dilution that I'm just going to use that round number. So the H3O plus concentration is going to equal, well, about 0.01 molar, right? Because it started at 1 molar and we diluted it by a factor of about 100, and so that's 1/100th of the concentration. Well, what is the pH if the H3O plus concentration is 10 to the negative 2? So the pH then is equal to 2.00, which is actually a pretty impressively acidic pH. We've moved 5 pH units. That means the H3O plus concentration has changed by 5 orders of magnitude, or about 10,000 times. Oh no, 100,000 times. So anyway, this is just to illustrate that for a regular pure water solution, even just a tiny addition of acid is going to change the pH by quite a lot. And if I added a base like NaOH instead, then it would have been increasing by 5 pH units, or it would have been a pH of 12. And so you see, just one drop, one direction or the other, swings the pH really wildly. So let me show you a figure here. This is figure 10.5. And what we're seeing is how the pH might change if you add some acid or you add some base to 2 different solutions. So the blue curve represents a pure water solution. You'll notice right in the center it has a pH of 7. And if you add a little bit of acid, that is going to the right side, the pH drops rapidly. If you add a little bit of base, that's going to the left side. The more base you add, the higher the pH rises. Well, the red curve is a buffer solution. This buffer is made by combining acetic acid and acetate ion, and those are a conjugate acid-base pair. The acetate is the same as acetic acid, just with the hydrogen removed. And it starts with a pH around 4.7 something. When you add the same amount of acid to that buffer solution, it just drops by a little bit. In the end, it's at 4.68 when the water had dropped all the way down to 2. And then if you add a little bit of base, then the pH rises, but only a teeny tiny bit. At the end, when the water had risen to a pH of 12, the acetic acid acetate ion buffer has risen its pH only to 4.85. And so you see this acetic acid acetate buffer solution has resisted changes in pH very effectively. So how do they work? They seem almost magical when you first encounter them, but they actually they make a lot of sense when you understand how they work. Okay, so you have in a buffer solution, you have roughly equal amounts of an acid-base conjugate pair. They're a weak acid and a weak base, and so they can interconvert between each other through this equilibrium reaction. And I guess there should be an H plus over on this side, right? And an H plus. And what we need to think about is what happens when I add acid to a solution which contains both of these in roughly equal amounts at equilibrium. Well, if I add a bunch of HCl, for example, to my buffer solution, then it's going to react with the conjugate base of the buffer, the acetate ion in the example we gave before. So that's going to be A minus, and that's going to produce HA plus Cl minus. So we started with hydrochloric acid, a strong acid, which in water would have donated its hydrogen 100%. And in this reaction, it was converted into the conjugate acid of our buffer system, which is a weak acid, which in water will donate its hydrogen maybe only 5%. And so this reaction has dramatically reduced the impact that we'll have on the pH by converting the HCl into HA. And if I were to add NaOH instead, if I add a strong base to this buffer solution, then it's going to react with the acid of that conjugate pair. So plus HA, and that's going to produce Na plus and A minus and some water. And again, we've taken this strong base, which was going to produce OH minus concentration, or OH minus hydroxide ions 100%, and it's been converted now to a weak base, which will go on and react and produce some hydroxide, but not very much, only maybe 5%, because it is a weak base. It takes a strong base and it converts it into a weak base, and that makes all the difference. So that is how acid-base buffer solutions work. Now let me put up this figure again. You may have noticed that the pure water, when you haven't added any acid or base, has a pH of 7 because it is neutral. But our acetic acid acetate buffer, when you haven't added anything else, it has a pH of like 4.7 something. So where does that come from? If you have equal amounts of your conjugate acid and base partners, then the pH is going to equal the pKa, or in other words, the negative log of the acid strength constant. So, one sec, I'll get the table of acid strengths up. Okay, so for acetic acid, we see that as 1.8 times 10 to the negative fifth. So what is the negative log? Negative log of 1.8 times 10 to the negative fifth. Okay, that's 4.74. So it's no coincidence that our buffer solution, and I'll pull it up again, give me just a sec. Our buffer solution that was made from acetic acid and acetate is centered around 4.74. You add a little bit of acid and the pH drops a bit below that. Add a little bit of base and the pH rises a little bit above that. And so, you know, the point of buffer solutions is to resist a change in pH. The point is to make a solution that will be stable and resist changes at a certain target pH. If you want a solution to be at 4.74 pH units and resist any deviations away from that, then acetic acid acetate buffer would be your choice. But if you wanted, for example, a solution that is buffered or held at a constant pH at something that is more basic, like 10 to the negative 10th, then you're going to want to choose a different acid-base conjugate pair. So the example I said was 10 to the negative 10th. Well, I'm going to look for a acid here whose Ka value is about I'm so sorry. If I want to hold a solution at a pH of about 10, then I'm going to look for a Ka that's at about 10 to the negative 10th. And it looks like hydrocyanic acid there, the second one, or maybe the very last one, the bicarbonate or hydrogen carbonate ion, 5.6 times 10 to the negative 11th. Those would be my best choices. And so I would take hydrocyanic acid, HCN, and I would mix it with an equal amount of cyanide ion, Cn-, that's its conjugate base, and I would get a solution whose pH is held close to the value of the pKa for hydrocyanic acid. Or in other words, negative log of 4.9 times 10 to the negative 10th, which is 9.31. It's not perfect, but it's close. So that's how you would choose which conjugate acid-base pair you want to use for your buffer. Now I'm going to give you one last really important equation here for the day. This is the Henderson-Hasselbalch equation. Okay, so the Henderson-Hasselbalch equation says that for a buffer solution, the pH is equal to the pKa plus the log of the amount of base over acid. And so this could be the concentration of the base over the concentration of the acid, or it could just be the number of moles of base over the number of moles of acid. It works either way. And so let's take our other example, our example from before. If I wanted to get a solution and I wanted to buffer it at a pH of 10, then I would put 10 here for the pH. And if I'm using the hydrocyanic acid, then it's going to have a pKa of 9.31 plus a log of base over acid. Now if I add equal amounts of base and acid, then this will be the log of 1, which is 0, and the pH will equal that 9.31. But I can fine-tune my buffer so that it has a pH that's actually equal to 10. I just need to solve for this ratio. So I'll take 10 minus 9.31. That's going to be 0.69. That's equal to the log of base over acid. And then in order to get rid of that log, I'll raise 10 to that power. And my ratio of base over acid then is going to equal 10 to the 0.69. It's going to equal 4.9. Or in other words, I'd want to put about 5 times as much cyanide ion, or 5 times as much Cn- as I put HCN. So maybe I'll put 5 moles of Cn- with 1 mole of HCN. And that's going to produce a buffer whose pH is precisely 10 and resists any changes to the pH as we add or acid or base. So buffer solutions are everywhere in nature, and in particular in our bodies. So there are a number of different acids and bases that are in our blood cytoplasm, in our blood plasma and in the cytoplasm of our cells. So one of them is a phosphate buffer. So if we have, hold up, I forget if it's phosphate or hydrogen phosphate. So let me just quickly look at the pKa's. Yeah. Okay, so one of them is H2PO4 minus in equilibrium with HPO4 2 minus. So we have both of these ions present in our blood plasma, and because of that, we can use the Henderson-Hasselbalch equation to calculate the pH. And then another is H2CO3 in equilibrium with HCO3 minus. And H2CO3 is itself in equilibrium with carbon dioxide and water. This is the classic vinegar baking soda reaction. Sodium bicarbonate is baking soda. You add some vinegar to convert it into carbonic acid, and then it will spontaneously produce carbon dioxide gas. So one of the results of this equilibrium here is that as we exercise and we breathe and we metabolize our food and whatnot, we are generating carbon dioxide in our bodies, and then we breathe to exhale that carbon dioxide. And ordinarily, our rate of metabolism and our rate of breathing and all of that is nicely balanced to maintain the pH of our blood. But if you're, say, a marathon runner and you're running for a very long time, well, you're going to be breathing heavily in order to get enough oxygen for your muscles to work. And it just happens that when you're heavily exercising, that balance is thrown off so that you end up expelling more carbon dioxide than you need to. And so you'll be getting rid of carbon dioxide too quickly. That's going to lead to a lower concentration of carbonic acid. And so your Henderson-Hasselbalch equation will now favor the base over the acid, and your blood will actually turn more basic than it's supposed to be. It doesn't take very much of a change in the pH of your blood to start really affecting things, because all of your enzymes, all of the cellular processes are dependent on pH. And so a marathon runner, among all the other problems that their body might experience through that arduous trial of running for so many miles in one day, well, one of the things, if they're not very well trained, is that their blood could become dangerously basic. And even if they are well trained, their blood will be at least slightly basic. On the other hand, sometimes you can be expelling too little carbon dioxide, and the opposite occurs. You get a buildup of carbonic acid, and then you get blood acidosis. And so having too much carbonic acid will make your blood pH lower than it's supposed to be. It will make your blood too acidic. And so anyway, these buffer systems, they're in our bodies, they're out in nature as well. The ocean and lake water, and in plants and animals everywhere, there's going to be some acidic or basic molecules that are at play, and trying to and effectively buffering that solution to be at a certain pH. So anyway, Henderson-Hasselbalch equation, I'll write it up here again because it is important. pH is equal to the pKa plus the log of base over acid. And let's do one quick practice problem. So I'll erase up here. We already went the one way. If I wanted to create a buffer that is buffered at a pH of 10, what's the ratio of base over acid that I need? Well, let's now do one where we're given a ratio of base over acid and we need to find the pH. And so HSO4 minus has a Ka equal to 1.2 times 10 to the negative second. It's a very, it's on the strong end of the weak acids. And that means that it's got a pKa equal to a negative log of 0.012. It's got a pKa of 1.92. So if I take 2 moles of sulfate and 1 mole of hydrogen sulfate and put them into a liter of solution, then what will be the pH? Well, the pH is going to equal the pKa, 1.92, plus the log of the base over the acid. Sulfate is the base in this case, so that would be 2 moles. Hydrogen sulfate is the acid, and so that would be 1 mole. So what is the pH? It'll be 1.92 plus the log of 2, and that's going to be 2.22. 2.22 would be the pH of that buffer solution. Okay, well, if this were a normal semester, I would do more with Henderson-Hasselbalch. There's really a great variety of complicated and interesting problems that we can ask, but for your upcoming exam and for the final, I'll keep your Henderson-Hasselbalch problems really simple. They'll be like the ones that we've practiced today. So I think we'll stop here.